All right, chapter 21, problem 26. We have a person with a body resistance of 10 kiloohms who accidentally grasped the terminals of a 20 kilovolt power supply. Draw a circuit to represent the situation. Well, the situation is simple. There's the power supply, all right, which is at 20 kilovolts. And then there's the person out here holding on to each end with their hair standing up on end. Alright, so that's part A. Part B, if the internal resistance of the power supply is 2,000 ohms, what is the current through the body? Alright, so now in part B we're talking about, we have our 20 kilovolts power supply, we have 2,000 ohms of internal resistance, and we have 10,000 ohms of external resistance. And that means that in part B, right, our total, which is R internal plus R external, is going to be 2,000 ohms plus 10,000 ohms. A kiloohm is 1,000 ohms, so 10 kiloohms is 10,000 ohms, so 12,000 ohms, right? And that means that the current equals V over the current, which is V over R total, is 20,000 volts, because 20 kilovolts is 20,000 volts, all right? All right, 20,000 volts divided by 12,000 ohms. 20,000 divided by 12,000 is 1.67 amps. All right, that's the current, 1.67 amps. All right, part C. What is the power dissipated in the body? Well, power is going to be, we're going to go with V squared, nope, I squared R. With I squared R. So we have 1.67 amps squared times the resistance of the person, which is 10,000 ohms, right? So 1.67 squared times 10,000 is 27.889 kilowatts, or 27,889 watts. I'm going to call it 28 kilowatts. All right, 28 kilowatts. All right, part D. The power supply is made safe by increasing the internal resistance. What should the internal resistance be for the maximum current in this situation to be a 1 milliamp, right? So again, we're looking at V equals IR, but we want I, all right, with 20,000 volts, we want I to be limited to 1 milliamp, or 0.001 amps, right? And that's times R internal plus, and we're still looking at 10,000 ohms on the person. Okay, so 0.001 amps times 10,000, 0.001 times 10,000 is going to be 10 volts, right? So on this side we've got 0.001 amps times R internal plus 10 volts. Okay, we subtract the 10 volts from both sides, and that gives us 19,990 volts is 0.001 amps times R internal. And if we just divide both sides by the current, we get R internal is 19,990 volts divided by 0.001 amps equals 99990 divided by 0.001. Okay, let's get that kicked over into scientific notation, because I'm lazy and I don't want to count zeros. today. Scientific, go with 4. Okay, so 1.99 times 10 to the 7th ohms are 19.99 kilo ohms. All right, 19.99 kilo ohms. No, sorry, 19.99 mega ohms. Mega ohms. Now, if you're one of the people that measured the resistance of your body from hand to hand in the lab, you found that the body's resistance is actually more on the order of 1 or 2 mega ohms, and not this 10 kilo ohms they have here. Okay, part E. Will this modification compromise the effectiveness of the power supply for driving low resistant devices? The answer is yes. On part E, the answer is yes. So imagine a low resistance device. Let's say that the resistance of the device is 10 ohms, right? Which means that we're going to get a total current of with this internal resistance, right? Our total is going to be 19.99 mega ohms plus, let's even go all the way up and say 1,000, 10,000? No, say 10 ohms, right? All right. So the current then is going to be the 20,000 volts divided by our total. All right. And so if we just take this equals that plus 10, right, we really make no difference in it at all. And 20,000 volts divided by that gives us a current on the order of a milliamp, which is what we were after. All right, current on the order of a milliamp, 1 times 10 to the minus 3, which is what we were after. If we didn't have that, right, our total resistance would be 2010, and our total current would be 20,000 divided by 2010 would be 9.95 amps. So this, since power goes as I squared R, this higher internal resistance is really limiting the amount of power we can deliver to a load. All right, and that's it for problem 26.